Hello, everyone. My name is Dr. Garrett Starkoff, and in this video, we will be talking about gases. On this slide, you can see an outline of everything we will talk about in the next few minutes. So what is a gas? Gases are a phase of matter where individual molecules are quite far apart. That's contrasted to liquids and solids, where the molecules are essentially touching each other. As a fluid, much like a liquid, a gas is also a fluid. The shape of a gas is the same as its container. I put a picture of some inner tubes on the lower right for you to see, bicycle inner tubes. And I think that you can understand that if you think about the gas, the pressurized gas that's inside of that inner tube, it's not all just sitting on the bottom or all sitting at the top. It fills the entire container because it's a fluid, it's a pressurized fluid that is filling the container, which in this case is a rubber tube. The volume and pressure of a gas is related to the energy of the individual atoms or molecules. So we said the molecules are fairly far apart as they run around and bump into each other. That is actually what creates temperature. So the temperature that you sense from a gas, whether it's a warm temperature or a cold temperature, is actually related to the amount of energy of those molecules bouncing around inside. Now, that interconnected relativity between volume, pressure, and temperature has been qualified by a number of gas laws over the centuries. And you may have heard of the ideal gas law. That's the one we use most commonly. There's also some other gas laws we'll talk very briefly about today. Now, you might wonder, why is it that engineers would care about gases? I mean, we're civil engineers, mechanical engineers, electrical engineers. We care about concrete and steel. But it turns out that a lot of things rely on gases too. So steam, diesel, gasoline, and engines, even nuclear power plants rely on gas fundamentals. They're common pollutants in the atmosphere, groundwater, and surface water. Gas impurities can weaken steel and concrete. Gases contribute to destruction of the ozone layer, climate change, sea level rise. All those are all related to gases in the atmosphere. And gases are imperative to human life. And if you don't believe me, hold your breath for even just 5 minutes. If you hold your breath for 5 minutes, you'll quickly realize that you really need gases in your life. And when we talk about gases, there are a lot of different ways we can describe the pressure that we sense. So for example, one atmosphere, if we look down here, one atmosphere is the pressure at sea level about. So generally speaking, if you go down to the coast, Newport Beach, and you measure the pressure right there, it's going to be measuring at about 1 atmosphere. Now that is equivalent to 14.7 psi. So a lot of times you look at the pressure in our car tires, for example. Car tires are typically around 35 psi. So it tells you that they're about double atmospheric pressure. Now, by the way, that's not an absolute measurement. That is a differential measurement, you might call it. So the absolute measurement would be 1 atmosphere plus whatever pressure you're adding into your tire. Not too important to think about that right now, though. But there are a lot of different ways. And as civil engineers, we also often use feet of water and inches of mercury or millimeters of mercury. And feet of water is the pressure that you would see. It's a kind of a pressure head. It's a pressure that you see if you were to push down on a water surface. You might see a pressure rise somewhere else, a head rise of water pressure. So I'm not going to go into the Charles law, the Boyle's law, and the Gay-Lussac law. But if you did look at those, you would see that they all are essentially broken down parts of the combined gas law. And the combined gas law is the one you see here. P1 V1 over T1 is equal to P2 V2 over T2, where P is your pressure, V is your volume, and T is your absolute temperature. Hopefully this is making some sense from chemistry classes you've had in the past. So let's do a quick example. You seal a rigid container at sea level at 20 degrees Celsius. You leave the container in a parked car that reaches 80 degrees Celsius. What is the pressure in PSI in the container once the temperature equalizes? Okay, so what we can do is look at our equation, look at our problem right here. We've got a pressure, kind of. I don't really tell you what the pressure is, but because it's at sea level, we know that that's about 1 atmosphere or 14.7 PSI. What's wrong with 14.7 PSI? We leave it and that's at 20 degrees Celsius. We leave it in a parked car, it reaches 80 degrees Celsius. So I'm starting to see we've got a pressure and a temperature that we start with. We've got a temperature that we finish with. We're not really given a volume, but what we're given is that it's a rigid container, which tells us that V1 is equal to V2 because it's a rigid container. If it was a flexible container, which you'll actually have later on in this lecture, that would change. Then your volume can change. So essentially, we can cross V1 and V2 out of our equation here. And what we want to find is what is P2. So our overall goal, what is P2? What's the pressure after we equilibrate our temperature? Okay, so first thing we want to do is make sure all of our units are consistent. So we have our pressure in PSI, 14.7 PSI is P1. P2 is unknown. T1 is not 20 degrees Celsius. If we put that, we would have a mistake because when we're talking about gases, we always have to use the absolute temperature. So T1 is actually 20 degrees plus 273. 293 Kelvin. Okay, so it's very important to keep that in mind. 293 Kelvin, and then T2, same deal, 80 degrees Celsius plus 273 gives us 353 Kelvin. Okay. And the reason that matters, by the way, is because you're talking about absolute pressure, absolute temperature. And so if it was at 0, that'd be the absolute minimum volume that you would see if it was the 0 Kelvin, I mean. But 0 Celsius is not the absolute minimum that you'll ever see. I mean, if any of you have been up on Mount Baldy or anywhere else where it's been below freezing, you've been in sub-0 Celsius temperatures. So it's not uncommon at all in a terrestrial environment. Okay, so P2, I quickly rearrange my equation here. It's just P1 T2 over T1. Just a quick rearrangement there. And that gives me 14.7 psi times 353 Kelvin divided by 293 Kelvin equals, and Kelvin cancels. Get my trusty calculator out. .7 psi. So it's increased by a decent pressure. If you were to open that up, you would hear something hissing. Moving on from the combined gas law, we also have the ideal gas law. And so ideal gas law is if pressure, volume, and temperature are related, then there's probably a constant that relates them. So we said before P1 V1 over T1 is equal to P2 V2 over T2. But what if we start thinking about that in terms of what kind of constant could relate them? And it turns out that constant also involves the material in moles, and that constant is R. So you may have heard of R before. If you think about the ideal gas law, when I think the ideal gas law, I think PV equals nRT, and R is just a constant. It's something that was measured. You know, it's a measured constant that relates the pressure, temperature, volume, and number of moles of a gas. And we use the word ideal gas. Most of the gases that you will deal with in your entire career are ideal gases. The only time it would not be an ideal gas is if the temperature is so low that you start getting interactions between the molecules, or if the pressure was so high that you had the same problem. But in regular environments that you and I are going to deal with as environmental and civil engineers, we will not have to worry too much about that. There are two different numerical values for R. One is 0.0821 or 0.08205. You can see there, and that's in liter atmospheres per mole Kelvin, or 8.314 joules per Kelvin mole, which is actually the same as liter kilopascals per Kelvin mole. Oh, and you know, I meant to mention before, a Pascal, put it on the slide earlier, it's just a Newton per meter squared. So that was something that on that slide, several slides back, where I talked about the different units that are used for pressure. I forgot to point out that a Pascal is a Newton per meter squared, but that's something to keep in mind. So note the units on R so that you know what units to use for pressure, volume, and temperature. And that's all you have to do. So if you know that your pressure is in atmospheres and your volume is in liters, use 0.0821 as your numerical value. You can also manipulate the ideal gas law. So we have all these different variables that are included. We can manipulate it to get volume on one side of the equation. So you can get V equals nRT over P. You can do pressure on one side of the equation. You can also even include molecular weight. So if you put molecular weight into the equation, you can essentially get an equation for density. Where rho is your density, m is the mass, and mw is your molecular weight. All right, makes sense, right? So let's have an example. Example number 2. A sample of nitrogen gas has a density of 0.25 grams per liter. if the temperature is 25 degrees Celsius, what is the pressure in atmospheres in the vessel? And I have your equation on the right that we need. Rho is equal to m over v equal to pressure times molecular weight divided by r t. Remember, that's two different variables there, r and t. So we need to just look at our equation here, or sorry, look at our problem statement and figure out what are the numbers we want to plug in. Okay, so we have 0.25 grams per liter. That's our density. Easy enough. That is the units that we will use. Temperature. We do not want to use 25 degrees Celsius because we're talking about gases. And so it's going to be 25 plus 273 equals 298 Kelvin. Okay. And we need our molecular weight. Now, I used nitrogen on purpose to kind of trick you a little bit. So just so you know, I'm tricking you. The molecular weight that we're going to use here is not 14, because that is the molecular weight of one nitrogen. But nitrogen gas is nitrogen 2, dinitrogen gas. So the nitrogen gas that's 80% of the atmosphere that you're breathing right now is N2, much like the oxygen is O2. What that means, though, is that our molecular weight is 2 times 14, which gives us 28 grams per mole. Okay, so now we have all of our variables that we need. We can plug it into our equation. We get that our pressure, I'm going to do a quick manipulation again here. So pressure is equal to density times RT divided by molecular weight. And so that gives us 0.25 grams per liter. In engineering, sometimes you do have equations that the units don't entirely cancel out. They're a little bit funky, but for gas laws, they do cancel out. So we can follow our units. R is 0.0821 liter atmospheres per mole Kelvin. Temperature is 298 Kelvin. And then our molecular weight is 28 grams per mole. All right, so I can go ahead and double check to make sure that everything cancels out like I think it will. Grams cancels with grams, liters cancels with liters, moles cancel with moles, Kelvin cancels with Kelvin, and I'm left with just atmospheres on top, which is exactly what I expected to see. So I can run my numbers here, 0.25, 0.0821, 298 divided by 28 gives me 0. 0.218 atmospheres is the pressure in this vessel. All right, I think that makes sense. And I should add, when you are doing these kinds of problems in the classes, for example, EGC 441 that you'll be taking in the program, we will often throw in, and this is on purpose so you can test multiple things at once, but we'll often throw in different units. So I might give it to you, I might ask you for the answer in terms of PSI, or I might give you the pressure, the density in terms of some kind of like milligrams per centimeter squared or centimeter cubed, and ask you to do that unit conversion too. And that's something you should expect to see. But I decided for this review lecture that we're doing here, I didn't want to include too much unit manipulation. So we're not manipulating a lot of units in this lecture. We are just looking at the gas laws and the calculations that are relevant to those. Another very important topic within gases is partial pressures. So if you think about a barometer is just a thing that's used to measure pressure. So the barometer shows results that are made up of many partial pressures. It just shows you the total pressure. So the total pressure, if you go down to the beach, is 1 atmosphere, which, like I said before, is about 14.7 psi or 101.3 kilopascals, and a pascal, if you recall. A Newton per meter squared. So that's a total pressure. At sea level, it's about 1 atmosphere. At a higher elevation, so for example, at the top of Mount Everest, it's 0.33 atmospheres. So it decreases by a lot. The total pressure decreases by a lot. But the total pressure is actually a sum of all the pressures being exerted by the constituent gases in the mix. So you guys know, I think, that if you look at the air that we're breathing right now, it's not just oxygen. And in fact, if you were just breathing oxygen, it would be like almost painful. It's so concentrated. So actually the air that you're breathing is about 80% nitrogen. It's about 20% oxygen. There's some argon, there's some CO2, you can see there at the bottom, there's some carbon monoxide, there's all kinds of different things in the gas that you're breathing. More argon than you might have thought. It's actually about 1% argon. But the partial pressure is very important for healthcare and environmental engineering. So we need to know what is the partial pressure of things when we're talking about how gases dissolve into liquids. If a gas is dissolved in a liquid, which happens all the time, it's happening right now in your lungs. The oxygen is dissolving across your lung membrane into your blood. CO2 is dissolving from your blood into the air so you can breathe it out. So it's very, very important for healthcare, and it's actually important for environmental engineering too, because we need to know how the pollutants are being absorbed into liquids so we can remove them from the liquids. We'll get into that in other classes, of course. But just want to let you know that partial pressure is a thing, and partial pressure, you can actually use the same ideal gas law. So I can plug in P1, for example, partial pressure of the first gas, into the ideal gas law and calculate the number of moles of that gas using the ideal gas law. Standard temperature pressure is another very important concept to take away from gas analysis. And that is that the standard temperature and pressure, whenever you're talking about gases, is 1 atmospheric pressure at 0 degrees Celsius. That's all it is. So just as long as you can keep that in mind, that it's about 273 Kelvin or 0 degrees Celsius and 1 atmospheric pressure, then we could bring any other measurement back using that combined gas law. T1 over V1 is equal to P2 T2 over V2. You can use that combined gas law to bring any measurement that you might have of pressure at any temperature back to the measurement of pressure at STP. And just so you know, at STP, 1 mole of gas occupies 22.4 liters of volume, and you can get that from the ideal gas law. Just plug in those values, 1 mole of gas, R, the temperature and the pressure, and you'll get that the volume will be 22.4 liters. It doesn't matter what gas it is. So you can see your helium, which is lighter than air, chlorine, which is denser than air, and yet they both have the same volume of 1 mole. So I threw in a couple of questions here to check some concepts, and I'm going to read the question and let you think about it for a second, and I'll tell you the answer. When climbing very tall mountains, is this true or false? When climbing very tall mountains, climbers need supplemental oxygen because the percentage of oxygen at the tops of mountains is lower. So think about that for a second. And think about it in terms of, would that make sense? If the percentage of oxygen here at sea level is about 21%, is there anything that would change to make the percentage less at the top of Everest? And the answer is this is actually false. It's not the percentage of oxygen that has changed. It's actually the partial pressure of oxygen. So we mentioned partial pressure. The total pressure, like we said before, drops to 0.33 atmospheres. So the partial pressure of oxygen is going to be that 21% that we expect times 0.33. And so instead of what your body expects to see of 0.21 atmospheres, so again, at sea level, that's about 0.21 atmospheres, your body's only seeing 0.07 atmospheres of partial pressure of oxygen, which means only 1/3 as much oxygen is getting across into your bloodstream. And that's why it's very difficult to breathe at higher pressures. Sorry, higher elevations, because it's actually lower pressure, not lower percent. Okay, next question. True or false? If the temperature is 40 degrees Fahrenheit in Minneapolis and 80 degrees Fahrenheit in Phoenix, it is correct to say that it is twice as hot in Phoenix. And hopefully by this point in the summary lecture here, you will know that that is also false. It's not twice as hot, because when you're talking about how hot things are, especially when it comes to gases and other things as well, metals and that sort of thing, you have to use an absolute pressure, or sorry, an absolute temperature. So if I said it was 200 Kelvin in one place and 400 Kelvin in another place, that actually is twice as hot. The temperature is twice as much at 400K than it is at 200K. So while 400 Kelvin is twice as hot as 200 Kelvin, 80 degrees Fahrenheit is not twice as hot as 40 degrees Fahrenheit, because those are not absolute temperature measurements. And the reason why this is relevant to a discussion of gases is because we might be tempted to say that a gas should have twice as much volume at 80 degrees Fahrenheit as it does at 40 degrees Fahrenheit, but it does not. If you recall from our discussion about changing from 20 degrees Celsius to 80 degrees Celsius, Even though that was 4 times as much in Celsius, our pressure only went from 14.7 to 17.7. So it wasn't a big change in pressure, even though it seemed like a big swing in temperature. Remember, with gases, you always have to use absolute temperature back to 0 Kelvin, not 0 Celsius or 0 Fahrenheit, which are much, much, much warmer. All right, and this is your practice problem for this lecture. I hope that this discussion has been useful for your classes.